potential vorticity, because there will be an effect introduced by the topography that can add vorticity to the flow. Okay. So what we saw the last time was another derivation of the Munk model, just starting from the primitive equations. The first two are the momentum equation, where we have introduced the horizontal friction components, okay, this 2 and this 2, together with the vertical stress component. Once we introduce this 2 and continuity, you can then vertically integrate your flow by defining the pressure field, the vertical integrated horizontal zonal component and meridional component of the flow. You integrate those equations vertically, you get to this expression where you have the vertical integral of the vertical stress component, and you set the vertical velocity to be equal to 0 at the top and bottom of the domain. Then, if you remember how the stress tensor was defined, was a component at the top and a component at the bottom for the x component and the y component. The one at the bottom is equal to 0. We're talking about a top Ekman layer where you feel wind stress, which is not felt at the bottom. So these two components are 0. And if you replace that expression into the momentum equation, then you get this expression for the vertical integrated flow. Okay, so you have the advection by Coriolis, the pressure gradient, the horizontal friction plus wind stress at the surface, horizontal friction, pressure gradient, and continuity. Now that we have set vertical velocity to be equal to 0. If again you take the curl of the horizontal momentum equation and use the stream function definition, then you recover the expression for the Munk model, okay, where you have advection by beta, you have an input of vorticity by the wind stress curl at the surface, and a removal of vorticity by horizontal biharmonic viscosity. Okay, important is that this simple model points to the role of the wind stress curl again, okay, not the wind per se, so it's the curl of the wind that injects vorticity into the ocean. It's not just the wind, so you need a curl. And the strength of the return current is dictated by the dynamics outside of the boundary layer. If you remember, the solution for the boundary layer correction was proportional to the wind stress curl. So the wind stress curl in the interior generates this verge of flow, and the return current is dictated by the wind stress curl in the interior, of course, because it has to balance this verge of flow. And this is why some boundary currents are different from each other, because they're all related to the wind stress curl in the interior of the ocean. Okay? So some western boundary currents are stronger than the other. The Gulf Stream, for example, is stronger than the Brazil current. They both are western boundary current. They are governed by the same dynamics, but they are governed by a different wind stress curl. So that's why not all western boundary current are equal. Okay? And so the western boundary currents here are the thick red arrows. Okay? You have a Gulf Stream, you have a Kuroshio, you have a Brazil current, you have an Antarctic current, and so on and so forth. Okay? They all follow the same dynamics given by these simple models of the wind-driven circulation, okay? The Stommel and the Munk model. In one model you need linear bottom drag, in the other model you need horizontal biharmonic viscosity. In both cases you need friction to balance the input of vorticity by the wind stress curl. Okay. How you can also interpret the need for a western boundary current is by using potential vorticity arguments. Okay. So if, for example, in this vertical interior of a subtropical gyres you have an Ekman pumping, so squashing of gas signals, the interior of the ocean wants to balance the input of vorticity, and it does that not by changing its relative vorticity, but by changing planetary vorticity. So it moves towards the equator in this case, to lower its own planetary vorticity. In order to return to a higher latitude within a western boundary current, you need to change F again. You need to change planetary vorticity again. And you need to put higher vorticity back into the fluid so that you can change F. Okay? This is not done by planetary vorticity because planetary vorticity is governing the interior solution. And so it has to be an input of vorticity by changing relative vorticity. And that's the solution that we found in the boundary layer correction. The boundary layer correction where you change is the relative vorticity, not the planetary vorticity. So if you're in the northern hemisphere of a subtropical gyre and you put friction on the wall, you can put your boundary layer correction on the west, or you can put your boundary layer correction on the east. Only the one on the west gives you an input of vorticity that balances the vorticity in the interior of the ocean. So if you use the Moog model where the meridional component of the velocity goes to 0 at the boundary and then it increases within a boundary layer, then this provides a change in relative vorticity that can balance the input of vorticity in the interior. If you put your boundary layer correction on the east and you set your meridional velocity to be equal to 0 at the boundary, then this will give you an input of negative relative vorticity that doesn't balance the vorticity change within the interior. Okay. So we always get to the same conclusion that if you have friction, in this case lateral friction, that change in vorticity is balancing the potential vorticity balance of the whole subtropical gyre. But again, this is not the cause of the boundary current, it's just a way of balancing vorticity. Okay? We will see that in a different model, you actually don't need much friction to balance vorticity. Okay? Okay. So now we'll introduce the effect of topography. Okay. So far we have assumed a flat ocean bottom, where the vertical velocity was going to 0 at the top and bottom. Okay. So far we have this. Sage, and the bottom was flat. Vertical velocity was 0 at the top and at the bottom. Okay. And so we derived the Zverjup solution, the Stammel model, and the Moog model. And by doing that, we could eliminate the pressure gradient, because the pressure gradient cancels out once you do the curl. The ocean is not flat, you actually have sloping sidewalls. So for example, something like this. And we'll put the sloping sidewall on the west because that's where we're gonna try to explain our western boundary current. And this will change the way we can think of the western boundary currents, okay? Because there will be an extra term due to the change in topography, the fact that now h is a function of x and y. Okay? And actually the solution can even become inviscid, so you don't need friction in order to balance vorticity, because you have an extra term due to the topographic contours. So if the ocean is flat, then the meridional flow within a boundary layer exists thanks to the frictional effects, permitting the flow to cross all the F contours, okay, that you have crossed before in the interior. But if the sidewalls are sloping, then the flow can move in a particular direction that we will derive, and you actually don't need friction because that particular direction is adding vorticity to the flow, which then balances the total potential vorticity. Okay. So now we're going to add to our model two things. One is topography, and the other one is stratification. Okay, remember that our ocean was always homogeneous, or it was vertically integrated. Okay, and we will see that the interaction between the pressure field that before was vanishing once we were doing the curve and topography can actually generate a meridional flow, because the pressure gradient doesn't vanishes, and so if you have a pressure gradient, you can generate a meridional flow. Okay, so now we define h to be a function of x and y. And so now we have our momentum equation that are this as before. Okay, you have the pressure gradient and you have some F where you have, for example, wind stress and frictional effects. We can now integrate this over the whole water column. And the bar is the vertical integration over the water column. Okay, so now you have integrated vertically the momentum equations. So now this wind stress curl and friction are vertically integrated, and now we are vertically integrating the pressure gradient. Okay, so now we will see that out of this term doesn't cancel out, and there will be an extra term. So if you remember Leibniz, where we were integrating a control volume, but actually here, so I used eta bottom. Okay, so this would be eta at the bottom, and this would be eta at the top. Eta bottom, the vertical integral of the pressure by using Leibniz is just this, this plus two terms, phi at the top plus minus phi at the bottom. Okay, so this is, if you remember, the Leibniz rule of integrating. Okay, so this term vanishes because we are setting eta at the top to be equal to 0. Okay, surface is flat, so that is equal to 0. And so this second term is now equal to that. Plus phi at the bottom. Okay, so that's my second term after using Leibniz. So we can go back to the vertical integrated momentum equation, and that can be written as this. So that's minus, so minus this plus the vertical integrated forcing term. Now we have this new term, which is the stress that the fluid is feeling because of the correlation between the pressure field and topography. Okay, so you have the pressure field and a correlation with the changes in topography, which is eta b. Okay, so the bottom topography changes in space, and so the correlation between the pressure field and the topography, we add an extra term to the equation. Okay, and this is actually called foam drag. I can actually govern the flow and constrain the flow a lot, depending on how strong the correlation is between the pressure field and the topographic relief. Okay, so now we can rewrite the this vertical integral of the pressure field. Okay, and that is, you have to be careful there. Okay, that actually, if you remember integral calculus, that is actually this minus h or minus eta minus h. Put here an h, which is the same thing. That is equal to this term minus z okay. But we know what this is. Okay, that's hydrostasy. Okay, and the first term is equal to 0 because z is equal to 0 at the top. Okay, so this is minus minus, so phi at the bottom h, bottom h, minus the vertical integral of z rho g okay, and we can call that term minus, but this is minus rho g, so this is plus E, which is actually the potential energy. Okay, so it's the vertical integral of rho g z, so that's the potential energy of the fluid. Okay, so now that we have rewritten the vertical integral of the pressure field, we can go back to the vertical integrated momentum equation, and we can write it as, okay, that one. Field is Z. Did I turn that on? Yes. Field is Z plus. Now it's Oh, yes, okay. So, minus plus, okay, so this is B grad H. Why is it grad H? Because this is an eta, okay, and grad eta bottom equal to minus grad H. Okay, because eta bottom is minus H. Big eta plus the vertically integrated stresses. And this is, we know this is equal to this. Okay. And this can be written as this vanishes with the other one, and then minus grad A plus the integrated stresses. Okay. This term goes away with the second term here, and so you're left with that. Now we want to get a Vorticity equation. So remember, this is still the vertical integrated momentum equation. Right? We want to get a Vorticity equation. So as usual, we take the curl and we actually divide by h. Okay, so you divide by h and you take the curl. And if you do that, take the curl of that, and you use the string function f over h plus this extra term h to the minus 1 potential energy equal to the curl of f over h. Because we have divided by h. Okay, you can recover the solution if you use the Jacobian. You can go back if you want. You can take the Jacobian and do if you expand the Jacobians, you will see that you recover this solution. It takes a little bit to just put all the terms together, but that's the solution. So this is the Vorticity equation that we get if we introduce a topography, which is a function space, and the stratification. Where is the stratification? The stratification is in the potential energy, rho g. Okay. So when we assumed a flat bottom and a constant density, we saw that the torque provided by the wind stress was balanced by a torque introduced by bottom friction. Okay. And that torque related to the change in planic vorticity, as in the Stoner model. Now there is an extra term because we have introduced topography and stratification, and that extra term appears because there is a combination between the stratification H, stratification E, and topography H. Okay. And that term actually has a name. Okay, it's called J-bar. That's the J-bar term, which stands for joint effect of baroclinicity and relief. We'll see that the J-bar term actually governs the flow in many places. For a constant h, and you can do this for a constant h, then, so if this is constant, the algebra term vanishes, and we can recover the Stonel problem. Okay. If this is 0, then you are back to curl of f. Okay, and this was the Stonel problem. Okay, so if topography doesn't exist, what's up? If topography is a constant, then there's no correlation between the pressure gradient and topography, and the algebra term vanishes, and you recover the Stonel problem. You can derive this in a different way by adding topography and stratification. And you can do that by eliminating actually this term, the potential energy, okay, which is less intuitive than the effect of the topography. So if you go back to the vertical integrated momentum equation, and you write that as V bottom minus grad E plus F, one of the steps that we found just before. And you take the curl of this, and remember that if you take the curl of this, you can show that the curl of H is equal to the curl of V bottom. Okay, by changing eta with H. So if you take the curl of this vertically integrated momentum equation, you get to the meridional advection due to beta, the curl of some forcing at the surface, minus this curl which is V at the bottom, and a gradient of topography. Which can also be written as curl of F minus the Jacobian of Phi. So there is an interaction between the pressure gradient and the topography. And now we have eliminated the energy term, the potential energy term. So this term is the pressure stress curve. Okay? And it's important to call it a curve because that is going to balance the wind stress curve. Okay? So this pressure stress curve is going to balance somewhere in the wind-driven jar the input of vorticity given by the wind stress curve. And we will see where this term is important. So instead of, remember the Stonel problem, we had some input of vorticity by the wind stress curve, and in the interior that was balanced by a change in F. And we had in one case a linear bottom drag or horizontal by harmonic viscosity. Now we have a pressure stress curve that is going to balance somewhere the input of vorticity by the wind stress curve. Now consider a much simpler case, homogeneous. Okay, so stratification is gone. Frictionless, which is where actually we want to go to, okay, a frictionless ocean. So there's not going to be any linear bottom drag or horizontal harmonic viscosity. And actually unforced. Okay, so there's no wind stress curve. There's no forcing at the surface, there's no friction at the bottom or at the sides of the basin, and the fluid is totally homogeneous. Then this equation reduces to this, right? So the curl of Windsor's curl and friction is 0, is a homogeneous, but we have already eliminated the potential energy term, so whether it's homogeneous or stratified, we don't care. It's unforced, it's frictionless, and so the vorticity equation reduces to that. And we have this, and now, so if h is a constant, then this will be 0, and meridional velocity will be 0. We're not forcing the ocean, so why should there be any meridional velocity? But now we have sloping topography, okay, which gives me a correlation between the pressure field and topography. And that is actually causing a meridional flow. Okay? That alone can cause a meridional flow. And you can rewrite this as this, okay? And so what is this telling you? This is telling you that there can be a meridional flow even if you are an unforced, frictionless, and homogeneous fluid. There can be a meridional flow if the pressure gradient, which is this term, has a component which is parallel to the topographic contour, okay? So that this term is not 0. If they were orthogonal, that would be 0. So this is not 0 if the pressure gradient or the isobars, they are parallel to topographic contours. So that means that the isobars are not aligned with the topographic contours, because you need the pressure gradient to be parallel to topography. Okay? So if you have a pressure gradient which is parallel to topography, then you can induce a meridional flow. Okay? And so in that case, if the isobars are not aligned with topographic contours, then the term, this term, is not 0. And you can induce a meridional flow. And so what is the meridional, how can you drive that meridional flow? That meridional flow is driven by the curl of the foam drag, that term here. Okay? So you have a foam drag, and the curl of that foam drag is actually driving a meridional flow. You don't need any forcing at the surface, and you don't need friction. The fact that you have a correlation between the pressure gradient and topography, which is not 0, drives a meridional flow. In a flat bottom ocean, so h is a constant and eta is a constant, then the foam drag is 0, and so this will be 0. It's not 0 if it is forced or if there is any friction somewhere. Okay, so this is how you can generate a meridional flow even without forcing the fluid and without friction. If you have a pressure, if you have a sloping topography, then the pressure gradient doesn't vanish, and that can induce a meridional flow, just because you have a correlation between the pressure gradient and the sloping topography. So if the pressure gradient doesn't vanish everywhere, then you will have a pressure gradient, and that pressure gradient will generate a flow, okay, without forcing the ocean at the top or with friction at the bottom or at the sides. So that would be an input of vorticity given by this correlation that somewhere will balance the input of vorticity by the Windsor's curve. And now we will see where this term is important. Okay? And that term is important along some isolines, which are isolines that are called F over H contours. So if we go back to the vorticity equation, which is this, f over h, then we had this extra term given by the stratification and topography, and that was equal to the curl of the forcing. Then take again a homogeneous fluid, so E is equal to 0. Forcing is 0, and friction is also 0. Then what is the vorticity balance for that particular case is just this. Right? So forcing and friction are 0, and it's homogeneous, so this term vanishes. So the vorticity balance is simply that. So what is this saying? This is saying that for an inviscid, so friction is 0, unforced, no wind stress curl at the surface, an unstratified flow, or homogeneous, then the stream function psi is a function of f over h. Okay. And so that is saying that for this to be 0, for the Jacobian to be 0, then the depth integrated large scale flow, or the stream function, has to go along f over h contours, because the Jacobian has to be equal to 0. Okay, so the stream function has to go parallel to f over h contours. And so f over h contours are just the characteristics of that partial differential equation. And this is also called a free mode, obviously. Makes sense? Free in the sense that it's not forced at the surface and there's no friction at the bottom. So it's free in the sense that you can have a flow that is not forced by an external agent, is just forced by the fact that you have topographic effects. And so this is a potential vorticity equation, and so that is obviously a statement of a balance between vorticity terms. And in this case, it's a balance between vortex stretching, because you're changing topography, so the whole vertical integrated, remember this is a vertical integrated momentum equation, the vertical integrated column of fluid, because topography is changing, then that vertically integrated column of fluid is stretching or squashing, right? Because of changing topography. And as it changes, as it stretches or squashes, then it has to change its total vorticity. Okay. So consider this sloping sidewall, okay, in a water column, which moves down the slope. So you have this water column, which moves down the slope. Okay, that vertically integrated column of fluid is moving down the sloping wall. As it does that, it wants to conserve its total vorticity, F plus relative vorticity. On a large scale case, okay, it's not going to change its relative vorticity, but it's going to change F, its planetary vorticity. Okay, it's not going to start rotating faster or slower, but it's going to change F. And so the balance on a large scale is just F over H, because the changes in relative vorticity are going to be negligible. And so in order to conserve potential vorticity, the column will be displaced meridionally, so it will change F as it goes down a sloping wall. So if H changes, F will have to change to conserve total vorticity. Okay? So in this case, the column will be stretched, and what it's going to do is it's going to move into the board in order to conserve its total potential vorticity. Right? So H is increasing, so F has to increase in order to conserve PV. Okay, so the flow will start to move into the board because H is changing. Okay. I guess you've seen conservation of PV in different cases. So if for example the flow is constrained not to change planetary vorticity, okay, and so you have Q is relative vorticity over H because, for example, it's in a canyon and it cannot change F. So if H increases, then relative vorticity will have to increase in order to conserve potential vorticity. Okay, so it will start to spin faster. If in a different case you cannot change relative vorticity, like in this case, you're not going to change relative vorticity, what you're going to do is change planetary vorticity, then the balance will be F over H. And so the column will not start spinning faster or slower, but will start changing planetary vorticity in order to conserve Q. Another case could be that you cannot change H because H is a constant, or again you're in a canyon and the topography is said to be a constant, so you have to follow that topography. If H cannot change, if for any reason that canyon is moving meridionally, so F is increasing, for example, then the column of water will have to start rotating slower in order to conserve potential vorticity. Okay. But we are here, we are in this case. Okay, so if you imagine your vertically integrated column of fluid moving down a slope in an unforced, frictionless, homogeneous fluid, this column of fluid, in order to conserve potential vorticity, will have to start moving meridionally, in this case, into the board, north. And start moving to the north in order to conserve PV. And it will do that, conserve PV, moving along F over H contours. Okay. In order for this to be zero, the streamlines will have to be parallel to F over H contours. And so the fluid will start moving meridionally and not in any way, but it will do that along F over H contours. Okay. The new F will be modulated by the thickness change H2 over H1. So the change in topography will determine the F over H contours. And so you will go as far north or as far south depending on the F over H contours. Now I can actually show you this. Okay. This is a map of F over H contours. Okay. So we know F, we know topography, so it's very easy to compute F over H. Okay. Maybe you can see the numbers, but the numbers don't matter much. What it matters is the path of those F over H contours. So imagine a constant F, a constant H, so a flat bottom ocean, for example. So in a flat bottom ocean, then F over H contours will be just flat. Okay. H is a constant, so you just have F as it changes meridionally. And so F over H contours will just follow latitude circles. And when do you see that? You see that in the equatorial region. In the equatorial regions, F over H contours are basically following latitude circles. Okay. But as you move towards higher latitudes, and especially you can look at the North Atlantic, which is the easiest place to see that, you see that F over H contours do something like this. maybe. Close to the yellow, close to the east coast of the USA. Okay, all these f over h contours, all this black thing is a lot of f over h contours sticking together, and they move meridionally, and then they cross the Atlantic in a way. Okay, and so this is where we will have our Gulf Stream. Okay. In that region, you don't need to force the ocean, you don't need friction. You have a strong correlation between the pressure gradient and topographic contours. So you have a strong Gerber term, and the flow will follow f over h contours in that region. Okay? And that will be the balance in vorticity that is required to balance the input of vorticity at the in the interior of the ocean. You can also see the Atlantic ridge here, how it changes the f over h contours, and here as well. So actually you can see bottom currents in the Atlantic Ocean that are actually following, instead of crossing, you have some zonal currents, okay? And instead of just crossing zonally the Atlantic Ocean, they actually follow f over h contours. Okay? There are observations of that, okay? Especially the bottom currents, which are filling the correlation between the pressure gradient and the topography term much more than the surface. Okay, so those are the f over h contours that yes.
Since the partial response in the meridional movement, I was expecting it to be not just.
Notice you have a meridional component of the flow, but that meridional flow is not totally meridional. It's following f over h contour. So the streamlines are now a function of f over h. And so that streamline will have to be parallel to f over h contours. And so it will go along f over h contours. And it will move meridionally, so it will change latitude. And it will do that by changing f over h contours in a particular region where that term is dominating and is inducing the meridional flow.
Might it be that the reason why the streamlines are fairly parallel in the equatorial region is because f is very, very small and close to zero?
Yes. So f over h contour is almost following latitudinal circles there. Okay. And so the effect of the Gerber term in the tropical regions is not very strong in changing the flow, whereas it's much stronger in the North Atlantic, North Pacific, close to a ridge, okay, where f over h contour is not following latitudinal circles, and if that term is dominating the vorticity balance, then the flow will follow f over h contours. It doesn't have to. I mean, that term, the Gerber term, could be much smaller than the other terms. We will see that in different places that term would be negligible, and in some particular places this term, the Gerber term, is actually dominating the vorticity balance, and so the meridional flow is actually governed by the Gerber term, and so the meridional flow in that particular region will follow f over h contours. Any more questions?
I'll ask a question that follows up from one of the questions I asked during that way.
Yes.
For example, around Namibia, there is I think it's called the Wallis Ridge. Close to Namibia, there is a ridge. I think it's called Wallis Ridge. If you see, there is a sharp gradient around that. That one.
Somewhere here.
Yes. So if the flow was to, if the flow was really so sensitive about the topographic effects. Now, with the presence of the wind, wouldn't that affect the upwelling system? Because in one of the papers I read, they were saying the ridge, talk about these effects that if they do happen, it means the flow is following the ridges, and if the water down there is kind of tends to be stationary. So even if the winds tend to blow over it, it tends to be the same kind of water because it is not changing. Because of say it follows, I don't know, it does not change. Therefore, it affects the upwelling, especially the biological sense of it, and then therefore you don't have a lot of fish that is produced. Could it be the tourism?
I don't think so. I don't think so because I mean here we're talking about large-scale vorticity balances, and I'm not saying that everywhere in this map the flow is following f over h contours. So these are f over h contours. In some places, the Gerber term, so this correlation between the pressure gradient and topography, is dominating the vorticity balance. And so the flow will be governed by the correlation between the pressure gradient and the vorticity balance, and so the flow will follow f over h contours. But in some other places, the vorticity balance might be governed by friction or by wind stress curl at the surface, and the Gerber term is negligible. So it's not that the flow has to follow f over h contours. If you have a strong ridge, that is a physical barrier to the flow. It might be a totally different explanation. It's not a vorticity balance. It's just that the ridge is physically constraining the flow. I'm not sure I understood actually the question.
I'm also really wondering whether the instances where the wind can overcome the topographic effects, probably.
Which is most of the places.
Probably not the surface, not into the interior.
Yes. Here we're talking about a homogeneous vertical integrated column of fluid. Right? So as I was saying before, you can find bottom currents that are following f over h contours or h contours, because you can consider that parcel of water to be unforced because it's not feeling the wind stress at the surface, and you can consider perhaps that parcel of water to be frictionless because friction effects are very small. And so that parcel of water might be constrained in order to conserve potential vorticity. As h is changing, that parcel of water will move following h in order to conserve vorticity. So the bottom currents might be governed by topographic effects, yes. Yeah. Not really. Yeah. So I don't know in that particular case what is governing the bottom currents, because you're talking about bottom currents, right? You're not talking about the surface. So another example is the some mesoscale eddies in the ocean. You can consider those mesoscale eddies to be quasi-homogeneous for 1,000 meters or even more than that, and they can feel the bottom pressure torque. And so you can see those eddies to go following f over h contours because they're strongly constrained the dynamics by the correlation between the pressure gradient and the topography. So there are dynamical systems that are affected by more than the wind stress curve, but it depends very much on what you're talking about.
So. What about the ACC in the Southern Ocean? Because I know that the flow of the ACC is from the surface to the bottom.
It's quasi-homogeneous. It's quasi-homogeneous, and so there is a strong free mode in the Antarctic circumpolar current. And so part of the ACC, especially close to Antarctica, where the wind stress curl is not the major input of vorticity. Very close to Antarctica, you can find a free mode in the velocities, and the velocities there are following f over h contours. So that's strongly.
I knew that in the Drake Passage, or eastward of it, there is a Scotia ridge, and so the flow of the ACC detaches in many different jets according to isobats. But it's not an enforced case. The wind is strong. So even though we have a forced gyre, we can have this flow.
You can have a contribution. You can have a contribution from the foam drag, from the bottom foam drag. Yes. And another question is when these f over h contours are closed, what is happening there to the vorticity balance? So the southern and this f over h contours, they close around Antarctica as well. So there's actually a very strong free mode in the Southern Ocean, very close to Antarctica, where the wind stress curl is not strong, but is not dominating as much, and the bottom pressure torque is actually very strong, and that constrains the path of the flow, which is actually following f over h contours. So it depends on where you where you are and what kind of systems you're looking at. In some places this term can be very important, in some other places it's not very important. But actually it can explain, as we will see, it can explain some, if not most, of the western boundary currents. Okay, last thing, we can look at the vorticity equation by looking at the linear vorticity equation that we derived many days ago. In which we had this linear vorticity equation, and if we vertically integrate again this vertical vorticity equation, we get the curl of tau at the top, which is the wind stress curl, minus the curl of tau at the bottom, which is friction, whatever friction you want to put, Stommel or Munk, minus a contribution of vertical velocity at the bottom. At the top is equal to 0, but the bottom is not, because we have a vertical velocity that doesn't vanish at the bottom because of the sloping sidewalls. Okay, and this is the term that we didn't have before without topography. Before we had a balance between the wind stress curl at the surface, some friction, and the advection of magnetic vorticity. Now we have an extra term, which is the stretching term, stretching of the column. We have a frictional term, and we have a, what do I call it? Torque by wind. And this is the change in F. So depending on where you are, one of these terms might be dominating the others and determine the vorticity balance of the system. You can go back to the same expression that we derived before in order to have the same terms that we're looking at, the vertically integrated frictional term minus the curl of pressure and topography. And considering both wind stress curl of the surface and friction at the bottom, the curl of pressure term and topography. Okay. So now we have first term, second term, third term, and a new term, which is given by the interaction between the pressure gradient and the topography. So if we set H to constant, we recover the solution that we had so far of Stommel and Munk. Now we have an extra term that can actually input vorticity to the system and balance the vorticity of the system. Okay, so the fourth term is the new one, and it's the important one. The important thing that you have to remember, you have a correlation between the pressure gradient and topography, and that can actually inject vorticity into the system. In an unforced, frictionless fluid, you can have a meridional velocity because of the injection of vorticity by the curl of the bottom form drag. So if we want to understand where these terms are important, actually this is a nice numerical solution. So it's a numerical solution for a homogeneous problem, flat bottom on the left, and a sloping western sidewall on the middle, so something like this. Okay, you put a sloping sidewall on the western side of your domain, and those are the stream functions that you get. Okay, this is the typical Stommel or Munk solution. Okay, here we have two wind-driven gyres, north and south of the equator, or actually you have a subtropical and a subpolar gyre. And this is the solution that you get when you include a sloping sidewall. Okay. And here, if you do an analysis of the numerical solution, you do an analysis and you look at the each component, so the curl of the wind stress, the magnitude of the curl of the wind stress, the magnitude of the frictional term, and the magnitude of the pressure stress curl, which is the number 4, you see that this term is important in these regions. Okay? And so in those regions where this term is important, the flow will be governed by this term and it will follow F over H contours. Okay? In these particular places, this term number 4 is very large because there is a strong correlation between the pressure gradient and H, because H varies very strongly in that region. So now we have these 4 terms, okay? And we can look at where these 4 terms are important in a simple, in the same 2-gyre solution. On the left you have, again, a flat bottom motion solution, okay? And those are the streamlines, and the dotted lines are F over H contours. So if H is a constant, F over H is just following latitudinal circles. So if H is a constant, in the interior flow, you have a Svargio balance, and you're crossing F contours. Right? You have an input of vorticity, and F changes, inducing a meridional velocity. So F changes, and the streamlines are crossing F contours. In a sloping, in a sloping topography case, F over H contours actually look like these dotted lines. Okay, you see they all converge here in this case, and then they go quasi-meridionally, and then they become following latitude circles, because here H is a constant. Okay. So where are these terms important? So in the interior you have the same solution. Okay, F over H is following latitude circle. This term, the Joubert term, is negligible. We said that in the interior of the wind-driven jar, the balances between the wind stress curl and the change in planetary vorticity. So here the solution is Virtual balance in both cases, okay, in the interior. So in the interior you have a balance between 1 and 2, between the wind stress curl and the change in planetary vorticity. Right? Then the streamline is going like this, is crossing F in its Virtual balance, then is in this particular numerical solution, then is reaching this region, and then is trying to go back to the north and close the gyre. And by doing that, it has to cross an F over H contour. So it has to cross H. How can you cross F over H contour? If you're governed by the Joubert term, you cannot cross F over H contour. You have to follow F over H contour. So in order to cross F over H contour, you need to balance vorticity by adding friction, which is the Moore problem. Right. So in this particular region, the balance is between 1 and 3. So frictional terms are allowing you to change F and to go back as a western boundary current, which is the Moore solution. Okay? And you're balancing vorticity. But then, after you have crossed the F over H contour, let's see if I can do it. Okay, these are the F over H contours. In the interior, you are in Virtual balance. You're crossing F, you're changing F, and you're balancing, well, you have a wind stress curl input of vorticity, and that is balanced by changing F, and you're crossing F contours. Then you're trying to close the wind-driven jar, and here you're crossing F over H. Okay, so here's the balances between 1 and 2. Here you're crossing F, so you're changing F. How can you change planetary vorticity? Is through friction. Okay? And that's the Moore solution. And that's how the streamline is able to cross F over H contours. Then what the wind-driven jar is doing is going along F over H contours. Okay, so here you're in Virtual balance, then you're crossing F over H contours. The balance is between the change in F and friction, which is Moore. And then the flow is going along F over H contours, and the balance is between 1 and 4. Okay, because here is where you have the sloping sidewall. The Joubert term is very important. This term is very large, and that gives you the vorticity to cross, to have a meridional velocity. And this meridional velocity is not just going north, but is actually following F over H contours. So the important thing here is that so the top by the wind stress drives the meridional flow across F lines, so that's the Virtual balance. The western boundary layer is then dominated by a balance between the meridional flow, so the change in F, and the bottom pressure stress curl. So this region in the western boundary is much larger than this region. Only where the flow crosses F over H contour is friction needed. Okay. And this happens where F over H contours converge and friction helps the flow to move across these F over H contours. Okay. So the important thing of adding topography is that apart from this small region, where you need friction to cross f over h contours, everywhere else in the western boundary current you don't need friction. You just need a sloping sidewall. That sloping sidewall helps you move meridionally. Right? This Gerber term, or bottom form drag, helps you to change f. So you can have a return boundary current that changes f just because of this sloping sidewall. You don't need any friction. You can be, in this region, is an unforced, frictionless, homogeneous fluid. It just moves along f over h contours because you have a sloping sidewall providing this term. Okay. So here you have Svarger balance, where you have Winster's curl. Here you have the bottom form drag, and only in this small place where you have to cross f over h contours you need friction. So the whole models of the wind-driven jars that were based on linear bottom drag and then lateral biharmonic viscosity, so they needed friction to balance the vorticity in the system. Actually, once you add a sloping sidewall, you don't need that friction, or you need that friction only a little bit in some places in order for the fluid to cross f over h contours. So the need for friction is very limited once you start adding topography and a more realistic situation. So the fact that the bottom pressure torque can play a more dominant role than frictional torque, so the bottom pressure torque is within the western boundary current, the bottom pressure torque is much more dominant in a larger region than the frictional torque. In order to close the vorticity balance in the western boundary current, that questions, of course, the physical relevance of the Stommel and the Moog model. There were very nice models that introduced a western boundary current, but they explained the western boundary current, or they were able to conserve the total vorticity just by adding friction. Okay? But that because it was a homogeneous or vertically integrated flat bottom motion. Once you add topography, that friction is not needed, or only a little bit of friction is needed to close the wind-driven jar. And so this is a nice solution of, on the left, a Sverdrup balance, which is where we started from, which is obviously not realistic on the western side, and a more realistic solution on the right, where you add is actually the full vorticity equation there. You have Winster's curl, you have friction, and you have realistic topography. And once you do all that, you get a much more realistic wind-driven jar, which is not as symmetric. You have a more realistic western boundary current, and actually you see how the western boundary current is following f over h contours, whereas in the Stommel and Moog problem it was just going meridionally along longitudinal lines. This is more realistic. The Gulf Stream, if you remember pictures of the Gulf Stream, it goes like this, right? And it crosses, and these are f over h contours. Okay?
I have a question. We opened the Panama Strait. We wouldn't have a change in the deep flow.
Panama Strait is not very deep.
Yes,
It's not very deep.
it's not.
No.
So I was thinking in the past, a few million years ago,
In the past, in the past it was deep.
it was.
Yes, I mean the continents were not attached, so it was.
It was very large, not tiny passage.
No, it was pretty big. I mean, it was going all the way to the bottom of the floor, and it was pretty large as well.
Okay.
I mean, there have been many numerical experiments where you close the Drake Passage because at some point in history the Drake Passage was closed. Drake Passage is between South America and the Atlantic Peninsula. Some millions of years ago, Drake Passage was closed, so the whole meridional returning circulation changes. And also the Panama Strait was open, so North America and South America were not connected. And that changed the path of the ocean circulation as well. So this is the end of the wind-driven gyres. So basically we went from a simple Virgil balance that explains why the subtropical, it was always a subtropical case, is moving meridionally, to then add in a boundary current. We found out that the boundary current is on the west. We thought that the boundary current was due to friction. Actually, friction balances vorticity. It's not the reason for the boundary current on the west. The reason for the boundary current on the west is Rossby waves squashing the gyre to the west. And actually, when you start including more physics into your model, for example, topography, you don't need that much friction to balance vorticity. The topography can inject vorticity into the fluid in order to balance the vorticity in the western boundary current. So friction, the need for friction is very limited. So friction is not that important in a more realistic model. Yes.